Today in class, we didn't make it all the way through the slides, so I wanted to take a few minutes to finish out the slides. That way, if you ran into questions on homework and you didn't want to wait until next Tuesday to hear the rest of it, you could watch this video. Okay, so we made it to this slide. What is engineering? We've talked quite a bit about it in class, that engineers solve practical problems using creative design and analysis processes. Engineers use different tools in order to solve those problems, and some of those tools would be mathematics, scientific principles, material properties, computer methods, and I think that's pretty straightforward. I think we all understand that pretty well. And so I kind of wanted to highlight what is not engineering. And so we've got tinkering, inventing, science, and math. And I think these are kind of misnomers out there in the community where people who are maybe not directly involved with engineering maybe see somebody who is very good at math as being a good engineer, or somebody who's really good at tinkering and trying to put things together is an engineer. So engineering, I want you to think for just a minute and think, why would I put on here that they're not engineering? Tinkering, inventing, science, and mathematics. Because I think a lot of people who are good at tinkering, inventing, and science and mathematics could be good engineers, but it's not the same thing, right? And so what is that difference? Well, typically in engineering, we want to use science and mathematics to solve a practical problem. And we want to use the science and mathematics to help us get to the most likely or the closest answer to an optimal solution. And so tinkering and inventing sometimes will eventually get us there, but it can be expensive if we were dealing with materials or equipment that is very expensive. And so we can't just try it, test it, measure it, test it, measure it. So a lot of times with engineering, we're trying to get to a solution using science and mathematics and avoid the tinkering, although there is a fair amount of iteration that does happen within the design process. And inventing is coming up with something novel. And so you don't have to be an engineer to invent something. And so those are also distinct. So here's a good example of a project, which would be an engineering project. And so this project was a senior design project a few years ago, where students in the mechanical and aerospace engineering department had to figure out how to pick up stickers from here and place them on these boards. So you can see there's 1, 2, 3, 4, 8 of these locations where they had to put stickers. So if we were to talk through this a little bit, this seems like an easy problem. I mean, for a human, it'd be easy. You just peel off the sticker and put it on there. And even positioning it would be very easy. But to train a robot or to design a mechanism that can do that can be more challenging. So typically when we talk through this in class, we talk about all those challenges. What things would you need to consider? What things would be important for you to keep track of? What would make this difficult? And typically what students come up with is pulling the stickers off of this paper might be hard for a machine to do, because what do? Do you get under it like you would a fingernail, or do you use a vacuum that will suction to the top part of the sticker? And if it does pull it away, then what happens with the rest of the sheet of paper? Does the whole thing lift up? How do you get those stickers off? And so there's a lot of technical issues just with peeling the sticker off. And then a lot of times students will also point out that the position of this sticker, where we pick it up, if we pick it up on this edge or in the middle, is going to determine where we place it on the board. And so if there is a requirement from the customer to place it in a specific location on the board, we're going to have these stickers positioned in the same place every time. And then once we pick them up, we're going to have some really repeatable movements from this mechanism. So you can see these students in the senior design or the capstone project course came up with this mechanism where they have a couple of servo motors which will rotate these arms, which then have these linkages going back and forth between these two motors on either side to position this in an X and a Y configuration. And then I suspect they have something in the Z direction also to make this suction move up and down. It's got a little suction cup on it. So there's a lot of things to consider here, like how are we going to program these servo motors to actually move to the position that we need them in an accurate way and a repeatable way so that the sticker gets placed in the right place every single time. And then we have some electrical connections that go back to a controller, which would need programming. We also have some considerations of material choice, like what if we made this linkage out of something heavy and then we're trying to get it to move very fast? Well, that might be problematic. The motors might have too much torque applied to them when it's trying to slow it down, or maybe it doesn't have enough torque to get it going if these bars are heavy. So we have a material choice. And then if we're hanging these things out here, these linkages, and we've got something that's sucking on here, we've got number one, the weight of the arm itself hanging out here, and then we have whatever mechanism is getting the Z motion to lift that thing up and down over the sticker and over the board. So that is going to have some weight to it. And so number one, we have to choose a material choice. We have to select a material that will allow us to have enough strength to handle that load that's out here. And then beyond that, we have suction that's happening. And so that's increasing the load when it's picking up the sticker. And maybe it's pressing down on here and increasing the load in the opposite direction. And every single time that it's doing a label placement, it has that cyclic loading that's going back and forth. And so we'd have to pick a material, and then we'd have to choose a geometric shape of that material and machine it into a shape to make it so it's strong enough, yet light enough to move back and forth. And then we also have suction. How do we turn that suction on and off? It looks like we have some more wires down here. Maybe we have some sort of camera that is looking at these stickers and placing this. So maybe we have some active feedback. So it looks at the sticker and it says, arm, this sticker is a little bit to the left of what the last sticker was, so we need to move it a little bit further. So then it translates that feedback from the camera through this wire into the controller, and then it tells these two-stepper motors to move in or out a little bit further. And then we have to obviously bring more sticker in. There's just a lot of complicated things here. So you can see that the problem we have requires some math, some science, materials, computers. There's a lot of things that go into solving something as simple as picking a sticker off here and putting it on here. So now I'd like to talk a little bit more about the different types of engineers. Now this conversation is very important. So I hope you find that this conversation will give you a little bit of insight or maybe add to your current thoughts on what these different types of engineering disciplines do. So aerospace engineers apply scientific and technical principles to research, design, develop, maintain, and test performance of civil and military aircraft, missiles, weapon systems, satellites, and space vehicles. And so aerospace engineers are also using that same science and technical principles. So that's why aerospace and mechanical engineers are pretty much the same undergraduate curriculum almost all the way through the program. It's because you're using the same science and same principles in order to solve problems, but now you're applying them to different problems to be solved. So we've got aeronautics where there are things flying through the air, and then we've got astronautics where they're out in the atmosphere, out beyond the atmosphere in space. And so there are different type of scenarios for these two configurations. So chemical engineers, a lot of times we think of chemical engineers as maybe somebody in a lab working on chemicals only. Chemical engineers actually solve a very wide range of problems, including biotechnical, chemical manufacturing, and they do plan and testing methods for manufacturing products and treating byproducts. They also can supervise production. So there's quite a few things that they can do. Chemical manufacturing, pharmaceuticals, even water treatment and oil refinery, they have chemical engineers in there who are defining the process. So essentially what they're doing is saying, we need these chemicals to go together at this temperature and pressure and duration in order for us to get the outcome that we want. And so they take chemistry and they apply it in a practical way to solve problems. And so a lot of times they will be solving problems in a wide variety of industries. Petroleum engineers. A lot of times petroleum engineers maybe are thought of as just out in the oil field trying to get oil out of the ground. Well, petroleum engineers do a lot of stuff from the very beginning all the way to the finished product. And guess what? More than just oil comes out of the ground. There are so many other things that come out of the ground that are useful to us in our modern society. And so petroleum engineers not only do the exploration and extraction of oil, but they also try to extract all the different things out of oil that can turn into other products. So almost every product that we use today has some oil component to it. So I mean, from clothes to cell phones to cars, not only just the fuel that they burn and the oil that's in the engine, but also all of the interior components, the plastics that we touch, all of the things that, I mean, there's just so many things that crude oil goes into. So I want to talk a little bit about the exploration and extraction. In the past, it was pretty simple. You would just pretty much just drill a hole down in the ground to where the oil was, and just like a straw, you'd suck it up right around where that straw is. However, several years ago, they came up with unconventional methods for extracting oil, which allowed them to actually turn that drill bit and go horizontal in the ground. So what that meant is instead of having a single straw pulling from the bottom, now you have a straw that's going horizontal and you're pulling from a whole bunch of holes in that, perforations in that line. And so you could have a string of pipe underground a mile long pulling oil in. So what that means is you'd have to have a lot less oil wells, which reduces the cost substantially, and also the impact to the location and the space that you're taking up above ground. And so instead of having oil wells very closely put together, now you can have one oil well that is very separated from others. The other thing that was developed around the same time that they had unconventional oil extraction was hydraulic fracturing. And so a lot of oil was found in this rock, very hard rock called shale. And so they figured out that if they put very high pressure water down there, they could break apart that rock into little fissures, and then they would pack it full of sand, and the oil could actually drain through those cracks in the rock, through the sand, and back into the pipe. So now you could get oil out of rocks that was not previously able to do. And so those two methods have really changed the game for how much oil we have, and it's made it so we can have so much oil coming out of United States that we could actually export it. Another thing I'd like to point out is where the water table is typically is much, much higher. I mean, this could be thousands of feet lower where the oil is pulled, and so it's independent of this water table that is much higher in the crust. So petroleum engineers are solving problems like this. This is highly technical. Getting a drill bit to go down through so many different layers takes a lot of material science, takes a lot of computer analytics, and then turning that and having it go through a layer that might be only 20 feet thick and have it go like a mile long, that is very challenging. That's a very tough problem. And so petroleum engineers do this oil extraction. They also do the refining of oil, which means they separate out all the components. So when you get out of the oil well, you have sand, you have oil, you have natural gas, and you have water. There's a whole bunch of other stuff that comes up too, but those are the primary constituents. And so you have to actually separate all those out. And then within the crude oil, you separate that into several different components, the butanes, octanes, and all the different materials that you would use to make other components. And so if you think about another crazy thing to think through is how many steps it takes from oil coming out of the ground until it makes it to your car, all the logistical steps, getting it refined, making it so it's clean enough, getting it into a tanker, getting that tanker over to a gas station, getting it into the ground, and then making it go up through a pump into your car. It's pretty mind-boggling how many processes are involved in getting gasoline to your car. Civil engineers. I think it's really important to note that civil engineers are the ones that are developing all the infrastructure and the things that we rely on a daily basis. And so construction of roads, buildings, airports, tunnels, dams, bridges, water supplies, sewage systems, civil engineers touch a lot of stuff that we rely on a daily basis. And so there's a couple of different projects that you can see here. But the challenge here is oftentimes they are dealing with materials that widely vary in their strength and their bearing pressure that they're capable of handling. And so there are some very complicated problems that are solved by civil engineers. And most of their products that they design require a stamp, a professional engineer stamp, because it directly uh, interfaces with the general public. Okay, so computer engineers, a lot of times we think this is what they're doing. They're just putting nuts and bolts into a computer, but really they do a lot more than just that. They can do computer chips, circuit boards, related equipment, software systems. They program a whole bunch of stuff, and really computer engineers is anything related to hardware and software of a computer. We typically will take a little bit of time at this point to talk through skills that your neighbor might have. So we will do that in class next time so you can get to know who your neighbors are. Maybe this is how we can find people with similar skills, similar interests. Okay. So a lot of times when we're talking through class, we talk about what makes a good engineer. Some of the qualities. So think about it. What are some of the qualities that you think would make a good engineer? And then how would you rate yourself on a scale of 1 to 10, or maybe 1 to 9 as it shows in the slide here? There are a lot of different qualities that make a good engineer. I suspect you're thinking about things like communication, maybe analytical skills. So here are some that we've compiled over time and I think are pretty important. Creativity. So engineers really are problem solvers and they need to think of outside the box and come up with new ideas. And so we spend so much time in the science of how things work so you can draw from that strength, that position of strength in when you're being creative in your designs. And then being able to communicate it is very important. And this is probably one of the biggest feedback items that we get from people in industry is the engineers that come out of Utah State are very well technically trained and they need a little bit more help and guidance on being good communicators. And so understanding, I had a professor when I was in school that said you need to understand everything in the governing equations, in the technical terminology, and in layperson terms. And I think that's a really good way to think about it because if you can communicate something at a technical level with other engineers, fantastic. You understand the governing equations. Now you understand what variables you're playing around with and what variables you can turn up or down to get the result that you want. And if you can translate that into something that anybody can understand, it's highly valuable. Excellent communication is very important. So start now, practice it a lot. Communicate with everybody, even if they're tired of hearing from you at the Thanksgiving dinner table. Being a team player is very important. Nobody is going to be able to pull off a truly large project by themselves. So you got to be used to working on teams. Meticulous. You can't afford to miss details. I know that people give us a hard time about being so detail oriented, but it's because the devil is always in the details, and we need to make sure that we are always looking at those details and how they might impact the overall outcome. Desire to learn. This is really important. I've always carried a packet of information around so I could learn more and more about specific topics. And I think that your desire to learn should not stop when you graduate. In fact, I think it should just be getting ramped up because there are so many things out there to learn. And the more you learn, the more you realize there's a lot more out there to learn. So it's really important for us to always continue to learn and think of how do we make something better? Are there alternative solutions to what already exists? All right, so let's get back into the discussion about the engineering disciplines. So electrical engineers, a lot of times we think of electrical engineer as designing Teslas, right? But they do way more than that. We see an electrical engineer in here. He's in a control panel. He's measuring maybe the voltage on these circuit breakers. There's a lot of different control components inside here. An electrical engineer is the one that selects these components. So maybe the customer comes to you and says, I want something to do X, Y, or Z. Well, the electrical engineer says, all right, in order to do that, I need all of these different components to work together, and then I need to program them in order for this entire system to work. Also, electrical engineers can be doing distribution of power. So this electrical engineer is looking at some medium voltage cables, very high voltage coming in through here. And they are selecting all the equipment, making sure it's installed properly. They're the ones specifying how to install it. So there's quite a wide range of what electrical engineers can do. environmental engineers, a lot of times maybe we put them into a category that is working on this sort of stuff. And sure, they do that, but that is a very narrow subset of what an environmental engineer does. So even in an oil refinery or a water treatment plant, they're doing a fair amount of work there to make sure that we are utilizing our resources properly, and they're making sure that, I mean, let's be honest, we can't just step away from all of these things that we currently rely on. And so how can we utilize our resources in a better way? How can we make sure that we're disposing of things in a safe way? We're just trying to prevent the impact that we're having on the environment. And so environmental engineers actually cover a lot more ground than people maybe think. Industrial and manufacturing engineers. So if you're manufacturing a million widgets, how do you make them faster? How do you make them cheaper? How do you manage the production? How do you lay out the production floor? All of that can fit under industrial and manufacturing engineers. Now, in this geographic location around Utah State, we have a ton of manufacturing, and quite a bit of it is done through automation. And so you can see a few robots here. These are work cells where somebody works here, probably somebody else works here and works here. This looks like injection molding to me. And so there's probably a fair amount of industrial and manufacturing engineering going on to make sure that these cells are ergonomically set up and uh, you know, optimized for high production runs, and making sure that people, machines, materials, and information, energy, all of that is optimized to make products at the lowest cost possible and a repeatable basis, so the quality is always very high. Materials engineers, we've got a snow ski here with a whole bunch of different components and different layers of it. So you can see this is a pretty good example of what a materials engineer would do. They've got all of these different layers. And so maybe they've got one layer that's metal, one that's composite, maybe one that's wood, maybe that one that's steel. And so they work with all kinds of different materials in order to create a product. And so some of the requirements are mechanical in nature, some of them are electrical, some of them are chemical. And so they're trying to find the right material or modifying a material to get the right properties, maybe these properties for the requirements that they need in order to make products work the way that they need to work. Mechanical engineers, best engineering discipline of all time, right? So mechanical engineers, I would argue, is the broadest of all of the engineering disciplines because we cover so much ground. A lot of times we have a pretty good understanding of a lot of different of the a lot of pieces of the other engineering disciplines. So there's power producing, power using. I mean, this is just so high level. All of these are pretty high level, but you can see that there are a lot of applications, a lot of industries that mechanical engineers can find a job. I mean, anything from aerospace all the way to banana production, right? So there's so many different industries we can serve and different ways that we can serve those industries. And so because we are in mechanical engineering, that's probably all I'm going to say now, because over the next several weeks in the class, we're going to talk all about what mechanical engineers do. So some different areas of interest within mechanical engineering, I will say a couple more things about it, is we have controls, dynamics, fluids, manufacturing, materials, thermodynamics. There's just so many different topics that we cover in order to solve practical engineering problems. So this little diagram's pretty complicated, but you can see that there's just a lot of different components that go into mechanical and aerospace engineering. All of the different subjects that feed into different areas in which we're supposed to be experts, or maybe we're trying to become experts in. But at the top here, we've got professionalism. So we take all of this science and we try to turn it into something that is professional through our ethics, economics, and communication. So in summary, these are some of the engineering disciplines that we've looked at today. There's a lot more out there. These are kind of the main ones. Hopefully you've got an okay feel now. I would strongly suggest, if you're a little bit blurry or not fully understand one of these, I would suggest you just do a Google search to find a YouTube video on where somebody's talking about a specific one. Maybe you're currently exploring the different options of different engineering majors, Maybe you want to hop on there and find out more about environmental engineering or industrial manufacturing or civil. You could spend some time seeing what those engineering disciplines do online. And I think there's so many good resources out there. That's a great place to start. Now, if you want to go deeper than that, you could set up a time with some practicing engineers. Look up online, maybe some civil engineering companies that are doing civil engineering stuff and see if they have time to sit down with you for 30 minutes. Make it easy for them. Make it so they don't have to do anything other than just show up in their office and talk to you about what they do as a civil engineer. There's a wide range for all of these of jobs that you can do, especially if you're willing and able to move to different parts of the country or even different parts of the world. There is so much need right now for engineers that we just don't have enough capacity to fill the demand. And that is just not even thinking about the people who are retiring. That's just increased workload across the United States. And there are a lot of people who are going into retirement over the next 3 to 5 years that is going to make that need even greater. So keep in mind that you might have to live somewhere else in order to do exactly the job that you want to do. That's okay. All right, I think that wraps it up for what is engineering.